Yay, you've reached the end. It's lesson 9.10, where we're going to talk about just one idea, the difference between absolute and conditional convergence. And of course, we'll do some review because it's the end of the year. Okay? So, key thing is, what's the difference between absolute convergence and conditional convergence? That's the key task today. So, many convergence series that you see have negative terms. Some alternate, or some have some other pattern, but they have some negative terms. Now, if you take the absolute value of each of those terms in that convergence series, well, that means all the negative terms just become positive terms, right? So, as an example, 1 minus a quarter plus a ninth minus 1/16. If I were to just remove the negatives, so make everything absolute value, that'd be 1 plus a quarter plus 1/9 plus 1/16, and so on. Okay. Now, when you make them all plus, it's less likely to converge because the sum is actually going to be bigger, right? In the one in red, we had this alternating part, so the sum should be pretty small because I'm adding and subtracting, adding and subtracting. Yet in the blue one here, yes, it's going to be always positive. The numbers are still getting smaller, but hey, there's a possibility that that sum will most likely be greater without those negative terms. Now, here's the thing. If the new positive series is still convergent, then we call the original series absolutely convergent. Okay, so if this blue one here is also convergent, then I say, oh yeah, that original series here is absolutely convergent. Okay, if, on the other hand, the new positive series diverges, so this one actually diverges, then we don't use the word absolutely convergent, we use the term conditionally convergent. Okay. So if a series converges after taking the absolute value of its terms, it is guaranteed to also converge with no absolute value. So I have 3 examples here, and I want you to just tell me if each of the following series is absolutely convergent, conditionally convergent, or, of course, divergent. All right? So we know that we should check the original series first. So if I check the original series for number 1, I see this is an alternating series, right? Terms alternate. I know that I have 1 over n. That is a decreasing, right? N goes to like infinity, 1, 2, 3, yeah, it decreases for sure. And then I should also check the limit as n approaches to infinity of 1 over n, and that equals to 0, so I know this converges by the alternating series test. The sum of n equals to 1 to infinity of negative 1 over n converges. Okay, so that's nothing new. Here's the new part. Now I need you to ignore the alternating part. Let's just pretend that all the terms are positive. So that means I now look at this series. So now we have to check the sum of n equals to 1 to infinity. And now it's 1 over n. Oh, I know this one. I've seen it so many times. Yeah, this is a harmonic series, or some people call it p-series, where p equals to 1. So therefore, this diverges. Okay. You can say by the p-series test, or just say by because it is a harmonic series. And because when I take the absolute value with the positive terms, this new series now diverges. That's right. We then can conclude, therefore, the sum of n equals to 1 to infinity of negative 1 to the n over n doesn't just converge, but we'll say conditionally converges, okay, or is conditionally convergent. All right, so once again, original one converges, the absolute value one does not. Therefore, call it conditionally convergent. Okay, so let's try number 2. Cosine n over n squared. Well, I'm thinking, how can I figure out if this converges or diverges? This is a kind of a weird term. I don't know. This cosine n really bugs me, but maybe I'll do some sort of comparison, because I can compare this to, I believe, 1 over n squared. Yeah. And I know that this 1 over n squared is a p series where p equals to 2. So therefore, by the p series test, this converges. Now, that still hasn't proved my original one though, right? So now I hope you can realize, note that cosine n is always going to be something that's less than or equal to 1. So I know that, hey, this is going to be less than. And what can I conclude from there then? So the bigger series converges. Remember, this is the bigger one, right? Bigger converges, therefore, yeah, the smaller one also converges. By what test is this? Yeah, so by the direct comparison test, DCT, I know that the sum of n equals 1 to infinity of cosine n over n squared also converges. Okay, now that was just the original. Let's now check. Okay, let's check. Check, check, check. What do I need to check? Well, I need to now check what the absolute value of that. Okay. And if you think about this, well, the absolute value here, well, hey, isn't that kind of the same thing as what I just did up here? Because doesn't the absolute value also is less than 1? Yeah, I think so. Okay. So by the same argument as above, we know by the direct comparison test, the sum of n equals 1 to infinity of the absolute value of cosine n over n squared also converges. So therefore, what can we say about the original function? I can give a little bit more space. I'll say, therefore, the original function, yeah, absolutely converges. Why is it absolute this time? Because the original one converges, the absolute value one converges, therefore this absolutely converges. Okay. Now you're thinking, I've got one more example here. This one must be the third case, so that's the diverging case. You're correct, but why? So you might want to just quickly do this. What's the limit as n approaches to infinity of negative e to the n over n to the e? Now notice this term here is exponential, so it's exponential growth. That means it blows up really fast, right? It goes to plus or minus infinity pretty fast. Really fast. Where n to the power e, I mean, that will get to infinity sooner or later too, but that gets there pretty slowly, right? So it gets towards infinity. I guess it's not even plus minus, it's just plus, right? But it gets there pretty slowly, especially compared to e to the x. So therefore, we know that this limit here, I'm not really sure what it actually equals to. I'd say it probably just equals to infinity, but I really definitely just need to show that this does not equal to 0. Okay? So therefore, by the nth term test, we know that this series, we got it, diverges. And if it diverges, forget doing the absolute value business, because who cares? It's not going to be convergent anyways. All right, so that concludes it. And I have seen questions like this on the AP exam, most likely on the multiple choice part of the test, but still you need to know the difference between these two terms. Okay, and the rest of 9.10 is review. So it's been a long unit. I think it's good if you can get back and do some review. Lots of different concepts here. This is a big doozy, and you'll definitely see most likely a free response question on this topic. Yeah, I think so. Okay. All right. Go practice, please.